by Dario Vincenzi, who is going to talk about elastic turbulence. And actually, can you share your slide?
Yes, sure. I wanted first to thank Christine and Rahul for giving me the opportunity to present this talk online, and apologize to the audience for not being there in person, but I had to change my plans at the last minute. So let me now share the screen. So the topic of my talk is the numerical simulation of elastic turbulence in a polymer solution. And this is a work that is based on the PhD of Sumitra Reddy Herazi, who finished her PhD last year in Nice. And it is a collaboration with Jason Picardo at IIT Bombay and Anupam Gupta at IIT Hyderabad. And it is funded by CEFIPRA, which is a Indo-French collaboration. So the main message that I will try to convey in this talk is that the simulation of elastic turbulence, it's a difficult problem, and it shows difficulties which are probably stronger than for Newtonian turbulence, and therefore one should have some extra care, should be extra cautious when one simulates elastic turbulence. So before entering the problem, let me introduce this phenomenon. Dhruv already discussed it on Tuesday. I will just say a few notions to set the context and introduce the main definition. So all of us know very well that for a Newtonian fluid, if we want to see a chaotic behavior, then the inertial effects should be stronger than the viscous dissipation. Or in other words, the Reynolds number should be sufficiently large. This is not the case in polymer solutions. Indeed, there can be purely elastic instabilities, which can trigger a chaotic regime, even if inertial effects are totally negligible, and therefore even if the Reynolds number is very small. And the first who introduced this denomination elastic turbulence is Victor Steinberg. Here I'm showing his first experiment, which is a von Karman swirling flow between two plates. The upper plate sets the fluid into motion. And as you can see, based on the size of the device, the Reynolds number is very small. Elastic effects are controlled by the Weissenberg number, which is the ratio of two time scales, tau, which is the relaxation time of polymers to their equilibrium configuration, and the ratio of tau to a typical stretching scale in the flow. So when the Weissenberg number exceeds a critical value or elastic effects becomes sufficiently important, we see all the features of a chaotic flow emerge. So here the Lyapunov exponent becomes positive. The power needed to maintain the flow strongly increases, which means an increased dissipation in the fluid. And there are power law spectra of the velocity, both in the frequency domain and in space. So power law spectra means that several scales are excited in the flow. And as Dhruv already stressed on Tuesday, the difference with Newtonian turbulence is that now these spectra are much steeper than for Newtonian turbulence. Therefore, the flow is smooth in space and in time, and it is more like a large-scale phenomenon, a large-scale flow. So one of the main applications of elastic turbulence is in mixing in microfluidics. This is because typically a microfluidic device would have a very small size, and therefore very small Reynolds number, and therefore a Newtonian fluid in a microfluidic device would be laminar. So different strategies have been introduced to enhance mixing in microfluidics, and the addition of polymers to a solvent is one of these strategies. Indeed, here is a nice illustration in one of the first papers of Reutemann and Steinberg. we have a serpentine channel with two inlets. The same fluid is introduced in the two inlets, but in one of the inlets, a colorant is added to the fluid. And then one looks at a certain distance from the inlet, whether the fluids have mixed or not. So in the absence of polymers, we see that the white and black fluids are still completely separated because there only thermal diffusion is active, which is a very poor mixer at small Reynolds numbers, of course. Whereas when polymers are introduced and the Weissenberg number, so elasticity is sufficiently high, we see that at the same distance, there is almost perfect mixing. This is due to this chaotic motion, which is triggered by elastic instabilities. Another application which is becoming quite, which is attracting a certain attention in recent years is elastic turbulence in porous media. So people have studied in a porous media how the flow changes when polymers are introduced and when the geometry of the pores is modified. And this is particularly interesting from an applied point of view because polymer solutions are indeed used in extracting oil from rock reservoirs. Indeed, these rocks are porous, and the addition of polymers can make the flow through the thin gaps between the pores chaotic, and therefore this helps the displacement of oil. Here is an illustration from a numerical simulation, and here are some recent experimental studies on this problem. So this is just a short introduction to elastic turbulence, to this chaotic regime, which is found in polymer solutions at low Reynolds numbers. And there are now three review papers that discuss this problem, especially mainly from the experimental point of view. If we look now at simulations, numerical simulations, we find something quite striking, which is if we look at simulations which are three-dimensional and in realistic conditions, they are very few, despite that this phenomenon is known for now 20 years. So we have one simulation in a von Karman flow, three-dimensional von Karman flow, some simulations from Komami's group on the Taylor-Couette flow, and the simulations on channel flows. If we add also simulations in 3 dimensions, but in a periodic box, we have 2 more simulations. This is the paper that Drubo discussed 2 days ago. So as you can see, I could count only less than 10 simulations in 3 dimensions of elastic turbulence. And this is more remarkable if we compare this number to the number of simulations that we have of polymer solutions at high Reynolds numbers. Over 20 years, probably the number of such simulations is 1 order of magnitude larger or even more. So what is the reason for this, why this simulation is so difficult? So to answer this question, let us look at how polymer solutions are usually modeled. So the building block for a continuum model of a polymer solution is the dumbbell model. So this is the simplest version of a polymer molecule, but it is the basis of the most common continuum models of polymer solutions. Typically, one focuses only on the slowest oscillation mode of the polymer. The 2 beads are the ends of the molecule, and the single spring models the entire elasticity of the molecule. And then one can write equations for the separation vector between the ends of the molecule and for x, which is the position of the center of mass of the polymer. So in the equation for the separation vector, we have stretching by the velocity gradient. The polymer is so small that only the gradients determine its deformation. There is a restoring force to equilibrium, which if it is linear, we talk about a Hookean dumbbell model. or if it is nonlinear, this force introduces a maximum extensibility. And then we talk about the finitely extensible nonlinear elastic model. In addition, there is a white noise, which models the fact that the molecules of the fluid collide with the polymer, and it causes fluctuations. The evolution of the center of mass is simply the evolution of a tracer with a given diffusivity. So starting from this microscopic description, one can move to a continuum description by introducing a tensor field known as the polymer conformation tensor, which is nothing but an inertia tensor of this system averaged over thermal noise. This average is an average over psi. And the trace of this tensor will be the mean square, R squared, will be the mean square extension of the polymer. Now, starting from this microscopic description, one can obtain a continuum description of the polymer solution, which couples the polymer conformation tensor with either the Navier-Stokes equations or here directly the Stokes equation, if I'm taking the limit of vanishing inertia. So here we can recognize in the equation for the conformation tensor the advection term, stretching term, a relaxation to equilibrium, relaxation which can be linear in the Hookean model, and then we talk about the Oldroyd-B model, or which can be non-linear with a maximum extension imposed, and we talk about the FENE-P model, where P stands for Pötterlin, because Pötterlin is the person who derived this equation in the nonlinear case. In this case, a mean field approximation is indeed required. And then we have here a Laplacian with a diffusivity, which is the same coefficient which was appearing in the center of mass, in the equation for the center of mass. This Laplacian is related to the diffusion of the center of mass, and it is usually a very small. Now, what are the properties of this tensor? This tensor is symmetric by definition. It is positive definite. This is an important property to be preserved in the simulations, because you can, if I go back to the equations, you can see here that if C becomes negative for some reason, then this restoring force becomes an amplifying force, and the simulation can blow up. It can become unstable if this positive definiteness is not preserved. There is a third property which was derived some time ago, but it has overlooked. It has been overlooked in the literature, which is if elasticity is linear, so the Oldroyd-B model, and we neglect polymer, the center of mass diffusivity, then the determinant of the conformation tensor must be greater than 1. So not only greater than 0, as positive definiteness would require, but even greater than unity. And this automatically implies that the trace of C must be greater than the dimension of space. Now, the exact mathematical result is a bit more precise, because this is a Lagrangian result, but I don't want to enter the details. Let us just say that if we start with an initial condition where the determinant is uniformly greater than unity, then it must stay greater than unity. And we'll see that this additional constraint can be used to guide our choice of methods in the simulations. So let me now come to what I was saying. Why is the solution of this model particularly difficult in numerics? The reason is related to this Laplacian term, because typically, if in realistic conditions, the diffusivity of polymers is really tiny. It leads to very large Peclet numbers, and which in turn would require very large scale separations, very large spatial resolution. Otherwise, we cannot resolve this dissipative term, which of course has a stabilizing effect on the simulation. So to my knowledge, the only simulation which has achieved a sufficiently large Peclet number is that of Alexander, which is still 10 to the power 5, quite still far away from some other experiments of Steinberg. So because of this, people who stayed with the moderate simulations, they have entirely neglected this dissipative term, because as I said, the realistic values of the diffusive scale associated to it would require a huge resolution and would not be resolved in the typical 256 or 512 simulations, and even much higher. So if one neglects this term, automatically the nature of the equation changes. It becomes hyperbolic. There's no dissipative term, and therefore one is faced with what is known as the high Weissenberg problem, in the sense that very large gradients of the polymer conformation tensor appear in the solution. So here is just a quick illustration of a 2D flow with a cellular forcing. This is the logarithm of the trace of C, which I repeat, it's the squared extension of polymers. And as you can see, in straining regions, there is very high stretching, which is highly confined. And therefore, one is faced with very strong gradients in this field, which can generate numerical errors in the advective term. And if these numerical errors can lead to a loss of positive definiteness of the polymer conformation tensor. And as I said, this can be the origin of instabilities. So faced with this problem, people have introduced several potential methods to address the numerical simulation of this equation when such a huge spatial resolution cannot be achieved. And here I divided these approaches into 3 possible classes. Sorry, before coming to that, I just want to mention one more point. And this is, there is one additional difficulty in solving elastic turbulence. It is that this problem is quite non-universal. Is much less universal, if you want, than Newtonian turbulence, and will lack a theory. So this is a point that also Drubo discussed in his talk. For example, let me talk about the spectrum of the velocity. We have a power law spectrum. The only theoretical prediction is due to Fuxon and Lebedev, which says that this power exponent would be greater than 3. But this assumption requires isotropy, which in a flow like this one might not be appropriate. And if we look at simulations, this exponent is found to vary over a wide range. Now, Drubo said on Tuesday that their simulations found an exponent 4, which was robust with respect to different choices of forcing. Nevertheless, there are several simulations in the literature which report very different exponents depending on the concentration, the boundary conditions, the forcing. Therefore, we lack a result which can guide us in saying, okay, my simulation is correct because I can reproduce it. So this makes the problem more difficult. So as I was saying, people have introduced different schemes, different approaches to solve elastic turbulence. Now, don't worry about the details of these simulations. The purpose of this slide is just to generate a kind of a sense of confusion in the audience. So if we start, one possible approach to preserve that positive definiteness, which is so important for stability, people have said, let us evolve the Cholesky decomposition. Let us Cholesky decompose the conformation tensor and evolve the Cholesky factor of it, or the symmetric square root of the conformation tensor, or a logarithmic representation of it and recover the conformation tensor through an exponential transformation which preserves positivity. Another approach is in reintroducing polymer stress diffusivity to stabilize the code and smoothen the field. But if we have a smaller resolution, necessarily for this approach to be effective, this diffusive coefficient will have to be quite large. And then people, much larger than the realistic values. And people have used a constant uniform diffusive coefficient, but also only locally when needed, depending on the eigenvalues of the conformation tensor or the local strain or the local gradient of the conformation tensor. And then there is the numerical scheme. One can use finite difference schemes with shock capturing approach if there is no diffusion, pseudospectral, or hybrid methods, lattice-Boltzmann for the Navier-Stokes and finite differences for polymers, pseudospectral for Navier-Stokes, or finite differences for polymers. And in addition to this, you may find some of these references in several of these categories, because one can do, for example, Balki et al., pseudospectral with global diffusion and symmetric square root, or Zanek, they use the lattice-Boltzmann plus finite differences with local diffusion and Cholesky, etc., etc. So there is a full plethora of possible approaches, which in itself is, of course, not a problem, because if we have different ways to address the same problem, that is only an advantage. It becomes an issue, though, if these approaches give different results. And so this is what I'm going to show, that some of these approaches give results which are different, even at a macroscopic level. I'm not talking about fine details of high-order statistics. I'm talking about the large-scale flow, the mean properties of the flow. So let me first address the use of matrix decompositions to preserve the positive definiteness of the conformation tensor. So the first one, which I'm going to consider, is the symmetric square root, which later I will abbreviate as SSR, this was introduced by Balki, Thomasis, Renardi, and Döring. And simply one decomposes the conformation tensor in this way, where B is symmetric. Then one evolves B and reconstructs C in this way, which preserves positive definiteness. This approach, in this equation, A is a free quantity. It is a matrix which just has to be antisymmetric. In 2 dimensions, it can take this expression to preserve the symmetry of the tensor B. And this approach has this decomposition has the advantage that the equation is quite simple, not very different from an MHD equation. And in addition, from a mathematical point of view, B is an element of a vector space, which was not the case for the tensor C. So this is the first one. Second one is the Cholesky decomposition. So starting from the tensor C, one can consider multiply it by the nonlinear restoring force in the elastic term and form this tensor J, and then Cholesky decompose it and evolve the Cholesky factor L. And these are the equations for the elements. Now, this approach, which was introduced by Vaidyanathan and Collins, is supplemented with a logarithmic transformation. Indeed, this decomposition remains unique as long as the diagonal elements of L stay positive. So to ensure this, they suggested to evolve the logarithm of the diagonal elements instead of the elements themselves, and then recover the original elements by taking the exponential. Therefore, the original elements remain positive all the way, and the decomposition is unique. But I want to stress the addition of this procedure in this approach, because we'll see later that it will play an important role. There is a third decomposition, which I will mention very quickly. So here, instead of sigma, please read C. It's the conformation tensor. So here it's an equation directly for the logarithm of C. And again, if one then takes the exponential, positivity is ensured. Here it is similar to the Cholesky one because of this logarithmic representation, transformation. So now I'm going to consider simulations of these symmetric square root and Cholesky decompositions in a very simple configuration. We are in 2D, the forcing is cellular. In the absence of polymers, this would be the vorticity field. And I consider this set of parameters and a moderate um, resolution, which is typically used in simulations of elastic turbulence. And the method I'm using, I won't use any diffusion here because of the small resolution. So I'm using a finite difference scheme with the Kurganov-Tadmor shock capturing scheme. This is was introduced to study hyperbolic transport equations. It has the benefit, the advantage that it can resolve discontinuities up to the grid size and then advect them accurately without any excessive smoothing of these discontinuities. It was adapted, this scheme was adapted to polymers by Vaidyanathan and co-workers, and it has become quite a popular approach. Here I'm citing just a few works by Prasad, Dhruba, Rahul, and then Pino and Da Silva and co-workers, and also Kumam and co-workers. There are several groups that have used this approach in the when diffusion is not used. So let us see now. I'm comparing. Is on the left is a movie of the trace of so it's the trace of C. Let me remind you, is the squared extension of the polymers in the Cholesky case, and in the right in the symmetric square root. So qualitatively, if we move to the steady state, we may see that it's a chaotic flow. It's a chaotic flow, and the cells get perturbed, etc. But if we look more carefully, we see that on the left-hand side, these cells stay more in place, where the orientation and size are more stable, whereas on the right-hand side, there is more deformation of the shape, the size, the orientation of these cells. Sometimes they even move other. So see, for example, here, there is this has increased in size. Sorry. We can see, or here, no, my ability of, I will let it run, but there are situations, if you look carefully, you will see that there is more deviation from the cellular structure in the right-hand side. So I can try. So to see this in a more quantitative way, we can, for example, introduce this parameter delta, which is simply a parameter which would be zero if the lattice would be perfectly periodic, and it deviates from zero when it is not. And as you can see in blue, it's the value of this parameter when the for the symmetric square root decomposition. And indeed, we see this increased with this greater deviation from the lattice here. Then we can look at the mean stretching. Mean stretching is greater with the SSR decomposition than in the Cholesky one, and necessarily the feedback on the flow is greater, therefore the kinetic energy is lower in the SSR with the Cholesky decomposition. Again, I'm talking about mean quantities, spatial means, nothing very, very precise, very fine. And another striking difference is in the mean polymer conformation field when I'm taking several snapshots and averaging there over time. As you can see, for the Cholesky decomposition, the mean flow is the mean field is not very different from instantaneous snapshots, whereas for the SSR decomposition, this is very different. The uh, the 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 field is smoothed out and it's much more symmetric compared to the Cholesky one. So even the mean field is really very different between the two. So the question we can ask is which one is correct? a priori, as I said, I have no mean to say which one is correct. But fortunately, we can use that condition I mentioned on the determinant of the conformation tensor. Indeed, if you remember, for the Oldroyd-B model, which I have been simulating so far, we, in the absence of diffusion, we have this constraint. And then when I calculate the minimum of the determinant of C over the domain as a function of time, I see that in the Cholesky decomposition, that constraint, that bound is preserved, is satisfied, whereas it is very frequently violated in the SSR decomposition. Now, to be precise, in space, the violation is tiny. It happens in very small areas of the domain, but very frequently in time. And the deviation is huge. The deviation from one is huge. So this is an indication that at the same resolution with same parameters, the symmetric square root decomposition is affected by numerical errors, which produce this additional deviation from the cellular structure, this breakup of the symmetry, this additional displacement of the cells.
Dario,
Yes.
excuse me, Alex Morozov here.
Yes.
Do you know what happens with this distance as you increase the resolution?
Yes, this is one of the points. The differences remain.
I see.
So
Okay.
it remains. And this is because let me comment on it later when I will have some more elements, because there is a reason.
Thanks.
So now, why this happens? The question why? If you remember, the Cholesky decomposition, in spirit, the two decompositions are similar. It's just the square root of a matrix. But the Cholesky one was supplemented by this logarithmic transformation, which is not there in the symmetric square root. So if by any reason, so this transformation was there to keep the diagonal elements positive. But if by any chance the diagonal elements stay positive by themselves, I could remove this transformation. It is not essential. And the composition would stay unique. So we did that. We saw that the diagonal elements remained positive, but the minute we remove the logarithmic transformation, we see that the dynamics becomes comparable to that of the symmetric square root. There is more deviation from the cellular structure. The mean field is more symmetric and smoothed out. There is increased stretching and violations of the bounds on the determinant. So the message that comes out of this analysis, the first message, is that it is useful to use a logarithmic transformation of the constitutive equation, because near to highly straining regions, which are in black in these snapshots, there can be exponential profiles in the polymer conformation tensor. And if we apply a logarithmic transformation, these exponential profiles are transformed into linear ones, which are much easier to resolve. So it is useful to use logarithmic transformations. Second point that I wanted to discuss is the use of artificial diffusion. So as I said before, diffusion should be in the equations from a physical point of view, because it's the diffusion of the center of mass. But what I'm going to discuss now is rather the use of artificially large diffusion as a stabilizing technique. I'm not talking about the physical diffusion. And indeed, in simulations, both at high and low Reynolds numbers, when people have used this strategy to stabilize the code, they have used diffusions which is much larger than the realistic ones. So the first approach that has been used was to use a constant coefficient kappa. And this is the first, and this is known as global artificial diffusion because of this. This is one of the first simulations. It certainly has the merit of being, I think, the second simulation of elastic turbulence. But let's see how this global diffusion with such a high Schmidt number can generate very large artifacts. I'm going to the steady state. as you can see, the cellular structure is completely destroyed. The dynamics is dominated by one single vortex, which moves around and change location later. So when one uses global diffusion, the artifacts can be extremely large if the unit number is so large. And in a paper with Anupam Gupta, we discussed the reason for this discrepancy. This is because when we have such a large diffusion of polymer stress, this very large polymer stress, which is found in straining regions, leaks into vortical region where polymer feedback would be negligible because polymers are not stretched there. So we find strong feedback in regions where the feedback would have been very weak otherwise. And this completely destabilized the vortical structure, etc., in a way which is not feasible. So this is more or less accepted in the literature, that global diffusion is artificial diffusion is not a good choice, even at high Reynolds number. And here are some references discussing this point. So people have then resorted to a different topic. If global artificial diffusion is too much, maybe we can use diffusion only when it is really needed, only when the gradient of the polymer conformation tensor is too large. And when we need to smoothen the field. And there are different options here. One is to introduce the Laplacian only when the eigenvalues of C turn negative. Or another option is to use an even hyper-diffuse term, but with a coefficient which depends on the strain, because the strain is what stretches polymers. When polymers stretch too much, then the diffusive term has an increased strength. Or a very recent approach was to base the intensity of the diffusive term on the local gradient of the polymer conformation tensor. We have seen that this is what causes problems in the simulations. So what the question is, this approach, does it solve, is it acceptable? Does it solve the problems which we found with global diffusivity or not? And I'm going to answer to this question in the next slides. I've compared this approach, the last one, because I find this approach more physical in the sense that the diffusion coefficient is directly related to the issue that we want to care, the large gradients of C. So here I have simulations where the Peclet number is infinite, so no diffusion at all. I'm using the shock capturing scheme, and the typical Peclet number, which is used when diffusion is implemented as a stabilizing criteria. And again here, we see in the transient that there are stronger deformations of the cellular structure. Again, I'm not good at playing movies, so I will stronger deformation of the cellular structure when we consider local diffusion. This typical snapshot shows it clearly. And at a more quantitative level, we can see again that parameter, which would be 0 for a periodic lattice and deviates from 0 when it is not. It shows stronger deviations when we have diffusion. And if we look at the mean stretching, this is increased, and there is a long transient before we reach the steady state, and the oscillations are much slower. And indeed, if we look at the power spectrum of the velocity, which is reported here, we see that when we have local diffusion, the dynamics is dominated by few large frequencies, small frequencies, sorry, whereas a wider range of frequencies is active when there is no artificial diffusion. So the second message I wanted to give is that even local artificial diffusion should be avoided because it can lead to artifacts. And the reason for this is that, yes, it's much better. The situation is not as bad as with global artificial diffusivity. But still, local diffusivity intervenes when the feedback is large. So it still diffuses, it still spreads large feedbacks, which are the most effective in the flow. So more or less the approach, the effect on the flow is of a similar nature, spreading large feedbacks, and so destabilizing regions which would not be destabilized otherwise. I have one last comment. What I wanted to make is about the effect of resolution. And here I'm also coming to Alexander's question. So we now took simulations with no diffusivity at the different resolutions. So obviously, if there is no diffusivity, when we increase the resolution, we see smaller and smaller scales appearing in the polymer conformation field. And this is clear in this snapshot. At the higher resolution, we see that the smaller fluctuations are present, and the regions of high straining are much thinner, much more confined. So now here my message is less clear in the sense that there are quantities, mean quantities, which seem to show a certain convergence when we increase resolution. Look here, for example, at the mean stretching. When we increase the resolution, we seem to achieve a certain convergence. The small scales, as I said, they cannot converge because we introduce larger and larger scales. But somehow intermediate scales seem also to have converged. But at the same time, you see here, for example, in the 2048 squared simulation, the energy content in the first mode is larger than for the others. And did you see that the shape of the cells seems to tend to be more squared than in the low resolution simulation? So the message that I can make is that for a qualitative simulation, low resolution is good enough. However, if we want to look at finer details, then one may want to check how these details can depend on the resolution. And to answer Alexander's question, suppose when we increase the resolution, we have more and more scale that form in the system. And here is the spectrum of the trace of the polymer conformation tensor. We have greater gradients. So the difficulty in resolving the velocity gradient remains and is probably amplified. So the fact that the differences between the Cholesky and SSR decomposition remain even there because we have created greater gradients. So this leads me to my conclusions now. So the ideal situation, of course, is to solve the full equations with realistic polymer diffusion. But given that the realistic Becquerel numbers are huge, this may not be possible, at least in the near future. And so if we use smaller resolutions, these are my 3 suggestions. The first one, use a logarithmic transformation because this allows to reduce the errors in solving potentially exponential profiles. The second is use a shock capturing scheme and therefore rather finite differences instead of a pseudospectral, and avoid any form of diffusion because this spreads large feedbacks where they should not be. Regarding this comment, if I'm allowed to make a joke, this is my contribution to this anti-diffusion workshop. And the last point is check what spatial resolution does to your simulation, because depending on the quantity observable you're looking at, it may be critical. Then, of course, I'm not saying that simulations which are not following this criterion are necessarily wrong. What I showed is with that flow possibly a worst case scenario. But what I'm saying is, if you have to write a new code, maybe it's useful to keep this kind of criteria into account. And so with this, I'm going to stop and thank you for your attention.
Thank you, Dario. Alex.
Hi, Dario. Thanks
Hello.
very much. That was very nice. I mean, my take on this is pretty obvious. One should just take the realistic values of diffusivity and be done with that. However, it requires a lot of resolution, and I understand your take. The question that I have is about your kind of the methodology in reaching these conclusions, because you're comparing against the bound that was derived in the absence of the diffusive term. Well, we know from the kinetic theory that this diffusive term has to be there because otherwise it's a singular perturbation. And so do you know what happens with this bound if one would include the diffusive term in the derivation, and wouldn't the problem go away if you do that? If you see what I mean.
So I've not done the derivation. This one is based on the characteristics of the PDE. The characteristics would become noisy in the random in the case of if one adds diffusivity. So I'm not. Maybe one could reach an average bound instead of a pointwise bound, but so this would be less useful, I fear. But what I'm saying anyway is, so this is just a way to detect the presence of numerical errors in the simulation. Whether this is not the physical bound which would hold for the real system is not important. It's just a way to detect whether I'm introducing numerical errors or not, independent of the scheme I'm using. I can try to use a Oldroyd non-diffusive simulation first to check if things are fine.
Thanks.
It's an indication.
Yes.
Towards the end, you had some simulations which I think you said had no diffusion at all, and yet you still had well-defined spectra. I mean, the equations are not very different to MHD equations. If you did that trick with MHD, it would just blow up. Well, how do you get a well-defined spectra at large K?
It's Kurganov-Tadmor. It's diffusive on the small scale. I mean, you don't include a diffusive term, but it's diffusive numerically on small scale.
Yes, sorry, I understood the last part, but I didn't understand the question.
The question was, I'm surprised that you could even get a sensible-looking spectrum if you've got no diffusion whatsoever. But maybe I missed what you meant by what you had in that calculation.
No, this is the Kurganov-Tadmor scheme, but there's no diffusion. But there are other simulations which show that this approach is good enough to well resolve the small scales. It's.
But I think there is viscous dissipation in this is a kinetic energy spectrum, not the polymer spectrum. In the kinetic energy
yes,
spectrum,
of
you have
course.
viscosity.
Oh, okay.
That sets up a
Yes, of course.
and that's why it's decaying faster there. If you had looked at the conformation spectrum, you would see a power all the way down.
It's here, you see.
Yeah.
But again, I mean, this is argument that was made by Mike Graham and if independently, they do not work together. Kurganov-Tadmor is diffusive at a small scale. It's a numerical diffusion that one does not control, but there is still some effective diffusivity there.
Yes, of course. I mean, that cannot be avoided. Yes. But this is why then things are converged.
Exactly.
Mm-hmm. But what I'm saying though, that effect is hopefully negligible compared to the artificial diffusion that I showed.
Other questions? Well then, if not, thank you, Dario.
Thank you very much. Thank you.